Okay, in this video, we're going to look at transformations of functions. Now, I'm specifically going to use quadratic functions to explore what each transformation is going to do to the shape and position of the graph, but transformations can be extended to any type of function that you may be working with. So even if you're not dealing with a quadratic, the way we approach it in this video can be extended to any of the functions that you may be looking at. So in terms of quadratic functions, we could have a number of different ways that it's presented to us. This is what we would call standard form. This would be a factored form and a vertex form. Now, vertex form is the form that actually shows different transformations on the variables in the equation. So we're going to pick this one apart and see how each of the values affects the shape and position of the graph individually. So for starters, we need to kind of look at the basic form of a quadratic function, right? So in the lowest form, an x squared term makes it a quadratic function. And I mean, it can get more complicated depending on different terms that you have added to it. But this will give us the basic shape of the graph. And then we can see, again, how each of the transformations are working. So this is going to be really important because we're going to look at to see how each value that we use affects this. So if we wanted to graph this, we could easily plot points. If you have no idea what it looks like, we can just pick a number of points and work from there. So generally, if we're trying to put it on the graph, we want to pick values that will show up near the origin. So picking numbers like 0, which is the smallest kind of number we can get, is likely to produce the smallest output. And values around it, like -1, -2, 1, and 2, will also produce small values. And hopefully we can get a sense of what the shape is and move from there. So nothing much going on here. If I wanted to know the y values that go with these x values, then I can just take the x value and square it. So if I square -2, that'll be like -2 times -2, which is 4. If I square -1, -1 times -1 is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So if I plot these points on the graph, on the coordinate plane, then I'll start with 0, 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. And then we can always just connect the dots. And we see that we have this kind of increasing motion on each side, right, to get that U, or what we call a parabola. But these 5 points right here, I'm going to use these extensively in this video. We're going to start off by plotting points to see the shapes, and then we're going to try to move away from using tables to graph these to understanding how each transformation affects either x values or y values in the function, so that we can just quickly produce a graph of this. So these 5 points, I'm going to call these anchor points, because these are the points that will essentially hold the shape of the parabola as we know it. So if we can look at how each transformation affects these values, then we don't need to plot the points in a table to get the graph going, but rather just move the values where we know they'll be. And this will be much quicker for us. So I'm going to continue to use this. As we move along, we're just going to see how this basic quadratic is affected by all the different transformations that we're interested in. All right. So in this example, it's not just y being equal to x squared, but y being x squared plus 2. So we want to see how this plus 2 is going to affect this, right? So just like before, the key here is to say that anytime we see a y value, we're going to let y be the same as x squared, right? So an x squared expression we're going to think of as a y value in terms of, is the transformation value affecting an x or a y? So in this case, order of operations is going to be the key here. And every transformation, if we were to pick an x, right? So I just have a sequence of x's available to us, right? We're not really sure how the 2 is going to affect this function, so we can pick a number of different points, plug them in, and get something out, right? But like I said, I want to focus on how this 2 is affecting this graph. So if we said that y was going to be an x squared value, in terms of order of operations, I would square these values first in order to produce a y, and then add 2 to it. So this added 2 is going to affect a y value. So we know that this 2 is going to affect this basic shape vertically because y's go up and down, right? So what I'm going to start with is to say that we're going to square the values first, right? So if I square negative 4, I'll get 16. If I square negative 3, right, negative 3 times negative 3 is 9. If I square negative 2, if I square 1, if I square 0, 1, 2, 3, and 4, right? Because I would square the x first, and then I would add 2 to that value. So when I square the x, I get 16. If I add the 2, 16 and 2 is 18, right? If I square the x first, then I would add the 2, right? So 9 and 2 is 11. So for each of these, I'm going to take each of the squared values and add 2 to it. So essentially, if I take each of the y values that we've already produced from my x squared value, right, adding 2 to this y value will increase each of the y values by 2, right? I mean, that seems pretty straightforward. That's a 2. So each of these y values that we already found on the graph, right, starting at 0, 0 plus 2 is here, right? And then 1 plus 2, right? Negative 1 plus 2, 2 plus, at 2 is 4, 4 plus 2, at negative 2, right, is 4 plus 2. So each of these points, each of these y's, added by 2 just moves each of these y's up 2 units. So if I were to make the graph, it's not actually changing the shape of the graph, it's just changing its position. So adding 2, as we can see, moves or shifts the entirety of the graph up 2 units, right? So this is going to be a shift up 2 units, 2 units, right? No change to the shape. That's important. No change to the shape, right? So same idea with this x squared minus 3. If we're looking to see how it's affecting the graph, right, we will start off by finding the y value, right, which we deemed as x squared. So we'll take the y value and subtract 3 units from it. So again, if I square each of these values, I'm still going to get the same values as my x squared original function, right? It's just that now that I subtract 3 units from each of these y values, then each of these y's will be decreased right? Y's go this way, will be decreased by 3 units. So here at 0, we can see the 0 value of the y goes down 3 units, right? The y value of 1 goes down 3 units, right? The y value of negative 1 also goes down 3 units because 0 minus 3 is negative 3, 1 minus 3, 1 minus 3, right? 4 minus 3, 4 minus 3. So the 4 minus 3 puts us at 1, right? 4 minus 3 puts us at 1. And it would carry on to these larger values, but we can see that the graph just gets shifted down 3 units. Right? So if we take our y value and subtract 3, this is going to just shift it because it's not going to change the shape. So it's just a shift down 3 units. Right? So if I took the original function and add a value or subtract a value, right, to the y's, each y value will either increase by 2, moving it up, decrease by 3, moving it down, but not changing the shape, right? Because this will be important later as we move through it. Right? So essentially we could add whatever. Any value we add to the y is just going to be a vertical transformation, either up for plus or down for 3. Down for a minus. Okay. So I have a lot of this one set up here, but let's take a look at it. So what we're doing here, in terms of order of operations, this one is going to, once we pick an x value, order of operations says we're going to subtract 2 first, which means that this transformation is going to affect the x values. So if we're taking values and trying to plug them in, then whatever this is going to do to this function is going to have an effect horizontally because x's move horizontally. So if I wanted to find the y's that go with it, I'm not going to square it first, right? I would need to take each of these and plug them in for x so that I can do the order of operations. So if I take negative 4 and plug it in for x, negative 4 minus 2, which is negative 6, then I would square it, is 36, right? And then I would keep going here. If I plug in negative 3, I would do negative 3 minus 2, which is negative 5. Negative 5 squared, 25, right? Plug each of these in. I'm just going to go ahead and plug them all in and then work them out since I have them all written out here. Right? Negative 2 minus 2, negative 4. Negative 4 squared. Right? Negative 1 minus 2, negative 3. Negative 3 squared. 0 minus 2, negative 2 squared. Right? 1 minus 2 is negative 1. Negative 1 squared. 2 minus 2 is 0. 0 squared. 3 minus 2, 1. 1 squared. 4 minus 2, 2. 2 squared. So if we're thinking about how the last set of transformations worked, when we added a value to the y, it increased the y's or shifted it up. If we subtracted a value from y, it decreased the y's or shifted it down. So at first glance, you might say, well, if the x is going to be subtracted by 2 before we square it, then a minus 2 should move it to the left 2. But if we look at the values, right, this smallest value at x squared was at 0. This smallest value at 0 isn't located until we get to 2. And then we can see that when it's 3, it's 1. When it's 1, it's 1. Right? 4, 4. 0, 4. So by the looks of it, it still was a shift because once we subtracted a value from these x's, the value is still squared, so we just kind of moved all these x's from the original function to like a new location and then squared them. So the outputs didn't change, right? We still have 0 squared, 1 squared, 2 squared, 3 squared, right? It's just moved to a new location. But like I said, the -2 mistakenly turns out where students will like to say, well, this moves it to the left because negative x's go this direction. But if we actually see what's happening here, the -2 is going to be a shift actually to the right. Right? So it's still going to be a shift because it doesn't affect the outcomes. Right? All of these values squared are still the same values. So we're still going to call it a shift, not changing the shape of the graph. But this is going to be a shift right 2 units. Okay. And if we look at this one down here, for a +1, again, I have it all kind of set up, so I don't have to write as much here. But I'm still going to plug in the -4 in for the x, right? And then I'll add 1 before I square it. So -4 + 1, -3. -3 squared is 9. -3 + 1 is -2. -2 squared is 4. Right? So if I keep going through this set, right? -2 + 1, -1 squared. -1 + 1 is 0. 0 squared. 1 + 0 is 1. 1 squared. 1 + 1 is 2. 2 squared. Right? 2 + 1 is 3. 3 squared. 3 + 1 is 4. 4 squared. 4 + 1 is 5. 5 squared. Oops. 4 squared. 4 squared. There we go. Right. So, again, when we take the x and add 1 to it, it's going to give us some new x, but those x's are still being squared. So again, we're still going to get 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. So the outputs are going to be the same. So it's not going to change the shape of the graph, right? At -1 is where that 0 value is. At -1. And then at 0, it's 1. And at -2, right? At -3, it's 4. And at 1. And then we can see that, again, the shape is still in the same position. So the shape is still the same, but it's been moved to a new position. So again, normally we would think, well, adding to x's would move it to the right because these are positive x's, but in fact it's going to be backwards from the way you see it. So a +1 is actually going to shift it backwards from what you would anticipate from x's, and it's going to move it to the left. So this is going to be a shift because it's not changing the shape, right? Left 1 unit. Right? So in terms of those anchor points that I mentioned at the beginning, right? If you see what's happening here, we're taking the original vertex, we're moving the vertex to a new location, right? Whether it was a vertical shift from the last page or a horizontal shift, right, in the x direction from these guys. But once you move that vertex, we can think back at this is the starting location of our original function, right? So if you remember what we had here, the original function had our 0 was our vertex. But then from here, if we were to go, right, from here, if we were to go out 1 unit, remember this is this x squared value. So if we go out 1, whether we square -1 or square +1, 1 squared is 1. And if we go out 2 units, whether it's -2 squared or 2 squared, both of those is going to be 4. So from the vertex, the anchor points are always going to be affected by how far away we move from the vertex. So 1 unit squared is 1, 2 units squared is 4, 3 units squared would be 9, and we can use these anchors to start moving away from these ordered pairs, right? So if we look back at what we had, right, we took each of these anchor points, right, off of the vertex. So if I move my vertex to the right 2 units, like we did here, right, then from here, if I move out, 1 squared is 1, 2 squared is 4, 3 squared is 9, and I'll start building this shape, right? So it starts off with, did the transformation actually affect the shape of the graph? In these 4 cases, no. So once we move the vertex to some new location, even if we moved it over here, right, left 1, then the anchor points, out 1, up 1, out 2, up 4, because 1 squared is 1, 2 squared is 4, 3 squared is 9. Right? Let's try a couple more transformations. Okay, so again, we want to think about order of operations. We know where we see an x squared as our y value. So in terms of order of operations, we would square values before we would multiply, because this is like 2 times x squared. So if we're producing an x squared first, then multiplying, then this 2 is going to affect y values, right? Because once I square it, it's still going to be the shape that we have, and then I'm going to multiply these y values by 2, so it's going to affect this graph in a vertical way, right? But we don't know at the moment if this is going to actually change the shape of the graph. So let's look at these from the points. So again, I'm just going to break this up into 2 pieces. I'm going to say, for these, I'm going to square them. So -4 squared, -3 squared, right? -2 squared, -1 squared, 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, right? Then I'm going to take and multiply each of these values by 2. So if I double the y value that we had, 16 times 2, right? 32. I'm going to double each of these y values, right? So each of the y values that we got, I'm just going to multiply them by 2, because that's, the next part of the order of operations, right? So 9 times 2, 4 times 2, 1 times 2, 0 times 2, 1 times 2, times 2, times 2, times 2. So if these y values are what we had here in this original shape, right? Now the y is like a y value of 1 is how many units this guy is from the x-axis. Because the x-axis represents y being 0, right? If this guy is 0, he is on the x-axis. This guy here at 4 is how far away he is from the x-axis. So if I'm doubling these y's, I'm essentially taking these distances and making them twice as far away. So this distance is fairly short, but if I double it, it's going to be here at 2, right? This guy right here is going to be at 2, like we anticipated, right? This distance is further away. So when I double him, he's going to be even further away, right? Zero's, doubling the distance of 0 isn't going to change anything because it's no units away from the x-axis. So when I double these points, the distance they are away from each other starting to change. So this 2 is actually going to change the shape. All right, it's not changing the position in terms of the vertex, but each of these distances are changing, so the shape is actually changing. Right? And we can think of this kind of in the same way if we looked at 1/2 x squared. Order of operations says we would do x squared first. So if I square each of these values, right, square each of these values, then I'll take half of it. So now I'll multiply by 1/2 each of these. But it's going to be the same kind of concept where each of these y values is the distance they are from the x-axis. So if I half this distance of 16, right, halving the distance of 9, I mean half of 9 I'll just say is 4.5, right, half of 4, half of 1, half of 0, half of 1, half of 4, half of 9, half of 16. So again, in terms of these heights, if we think of it like this, I'm taking half of this height, which is a half, right, like right there. Half of this height of 4 is 2, right? Half of this height, half of this height of 4. Half of 9, we said, was 4.5. So if I go out 3, normally I would go up to 9, but I'm going to go half of that height. So 1, 2, 3, 4, and a half, right? If I went up 16, half of 16 is 8. 1, 2, 3, 4, 5, 6, 7, 8. So you can see that, again, and half of 0 is 0. Again, it's going to change that shape, right? But each of these heights is shortened. So the shape essentially gets wider. Actually, it goes through right there, right? Okay. So let's try to consolidate this a little bit, right? So if this coefficient is a multiple to a y value that represents the height, then the height will increase if this coefficient is a value larger than 1, right? So in terms of like standard form, right, I'll just call this A, right? So if A is bigger than 1, then it will have an effect on y's, and y's are vertical components. So I'm going to say this is a vertical alteration to the graph, okay? And in terms of the vertical aspect of this, it's going to take each of these values and stretch them vertically. So I'm going to call this a vertical stretch, right? Whereas this guy, his A, right, if A is a value less than 1, meaning if this is 100% of the height, if I wanted to take some lower percentage, if you want to think of it in percentages, if A is less than 1, then it's still going to affect the graph vertically, right, because it's affecting a y value, right? X squared, we said, was y. Then I'm halving it. So it's going to have a vertical effect on the graph. But we're going to call this, in terms of y's here, I'm going to take these y's and I'm going to compress them down. So we'll call this a vertical compression. Okay. Now, stretch and compression are dependent on your point of reference. Again, since these are vertical values, because they're affecting y, if I take the graph and pull it and stretch it, then it will get thinner, right? So we can say that a vertical stretch visually will make the graph thinner, whereas if I took these y's and pushed down on them, compressing, it would widen the parabola, right? So I'll call this, as a visual aspect, it's going to make it wider. So a lot of times people will say, well, you know, the 2 makes the graph thinner and the half makes the graph wider. That's fine, but a vertical stretch is the more specific way, right? Definitive, kind of by definition, what it's really doing, right? So again, we can see these guys affect y's. Certain of these transformations are affecting x's. So it's either going to have a horizontal component if it's on an x, a vertical component if it's on a y. Let's look at another one. Okay. So again, leaning on order of operations to try to get a sense of how the values are going to affect the overall shape, right? What kind of effect is this transformation going to have, right? So there's no difference between looking at this and, say, looking at this, which, you know, you might have done a long time ago when you first introduced, like, negative values, right? So in terms of order of operations, we would square the x first, then do multiplication, right? So we don't need to write the 1 here, but we know that this is going to be a multiplicative value versus the exponent. So in terms of order of operations, we are going to, again, square each of these values first, if we wanted to think of it that way, right? And then we'll take the opposite of it. So if I multiply each of these by -1, it's just going to change the sign, right? Times -1 is just going to be -16, right? This will be -9, -4, -1, -0. Doesn't really make any sense, but that's all right. -1, -4, right? So in its standard position, each of these y values had a distance from the x-axis, and it's still going to be 16 units from the x-axis, 9 units from the 4 units, 1 unit from the x-axis. It's just going to be from the x-axis on the bottom. So instead of 1, it's now -1. Instead of 1, it's now -1. Instead of 4, we got -4, -4, right? -9, -9. So the shape didn't change because the values of y are just negative versus positive, but they're still the same distance apart from one another, right? So again, this transformation isn't going to have any effect on the shape, right? But since it affected y's, it will have an effect vertically, right? And if you look at it, basically we just have each of these points get transformed across the x-axis to a new location. Even this 0, since it's on the x-axis, didn't actually change because the opposite of 0 is still 0. So what we'll say is that this had an effect that is a reflection, and more specifically, y values are on top and bottom of the x-axis, so this is going to be a reflection over the x-axis, right? So a reflection over the x-axis, if you think about it, has that vertical component because we're going from the bottom of the graph up to the top or vice versa, right? So it's still got that kind of vertical component to that, okay? Now this one, I kind of left a space here because in terms of order of operations, we would need to take the opposite or multiply each x by -1 first before we square it. So this guy is going to have an effect on x's, right? I mean, I can say that whatever x I pick, I want the opposite of that, right? So the opposite, or a negative times a negative, if you want to think of it that way, is a positive, right? The opposite of 3, -3 is 3. Opposite of 2, 1. 0 is still 0, right? Opposite of 1 is -1, or a 1 times a negative is a -1, -2, -3, -4, right? Then we would square these values. But again, squaring 4 is still going to give us 16, still going to give us 9, 4, 1, right? So the outputs, again, are still the same. So it's not having an effect on the shape of the graph, right? But in this case, changing all these x's to its opposite component, whether it be negative to positive or positive to negative, basically just took each of the x values that were over here and put them on a spot over on this side of the graph, but then we still squared it. So if I had 1 squared, which is -1 squared, which is 1, now it became 1 squared, which was 1, right? And vice versa. If I took a 2, I made it now into a -2, but when I squared it, I still get 4. So all of these values still lie right on top of this basic shape, right? But you can kind of see what's happening here. right? These values took each y and changed it from a positive y to a negative y. So positive y's up here became negative y's down here, which was our reflection over the x-axis. This guy is going to take each of the x's, which are over here, right, and move them or flip them to a position over here, so it's going to be a reflection over the y-axis. Now, this parabola is already symmetric to the y-axis. So a reflection over the y-axis in this sense doesn't actually put it in any sort of new position because of its symmetry, right? But if we were dealing with a function that wasn't symmetric to the y-axis, then this would have an effect on its outputs, and it would put it in a new position, right? Just like this guy wasn't symmetric to the x-axis, which is why it actually created a reflection. So depending on which functions you're dealing with, if you're dealing with other functions rather than quadratics, you might actually see an effect. Now, there is one thing to note here that, if I wanted to take negative x squared, these transformations aren't going to be quite as common because in the sense of operations here, we could simplify this, right? Because this guy is the same as negative x times negative x, and a negative times a negative is a positive, so it's basically x squared, which is why the outputs here are the same for the original function. So sometimes these operations are transformations that are kind of inside the parentheses, affecting the x, may not be quite as common if you're reviewing it in your class, because we can easily simplify this to some other form, right? But it's good to know what's happening to the function in the case that you just want to think about this transformation in terms of like any function in general. So, because these are transferable, like I said at the beginning of this video, these are transferable to other types of functions. So knowing that if you take an opposite value of a y, we'll reflect it over the x-axis, taking the opposite value of an x reflects it over the y-axis, right? But again, in terms of those anchor points, right, looking at this guy, if we looked at the anchor points being, from the vertex, always from the vertex, out 1, up 1, out 2, up 4, knowing that we had a negative in the front, and it reflects it over the x-axis, just means that the position of these anchor values are going to be the same distance from the origin. It's just instead of going out and then up, we're going to go out and down 1, out 2, down 4, out 3, down 9. So once you start using the anchors as values that you know its position based on its shape, then you can say, well, does this transformation affect the shape? No. Then once we know where the vertex is, then we can start building the points without these ordered pairs and get the shape much easier, right? If it is going to affect the shape, then once we move the vertex to a new location, then we say, well, if I'm going out 1 and then going up 1, if I have a multiple of 2 here, instead of going up 1, I'm going to go up twice as much. So I'm going to go up like 2. If I normally go out 2 and then up 4, I'm going to go up twice as much, which is 8. So I'll use the anchor points a little bit more in the next video that I make, which will start putting these transformations together. So if you're interested in that, you can kind of look at that, and then we'll put these transformations together, graph these things, and try to get away from plotting points, which is very time-consuming. All right?